Hey, good morning, everyone. Glad to be here. My name is Kyle Ingersoll. I'm currently an undergrad research student at Alfred State. Today I'm going to be talking about some eco-friendly concrete, utilizing recycled glass and alumina waste in the mix for a more sustainable construction. So we're going to talk about some background and motivation, our current idea, some of our sample and testing, and then we'll look at the results and make some conclusions there. So the original idea for this project came from Governor Kathy Hochul's announcement in 2023. She's put over $20 million in funding work for sustainable management practices in conjunction with the New York State College of Ceramics at Alfred University. This is the school that we partnered with. They're right across the street from Alfred State, so it works out quite nicely. And they are the #1 school in the nation for ceramic engineering and I think #2 in glass research. So they're a big deal. We're very fortunate to have them so close and willing to help us out. But so this was kind of the motivation. The governor pushing for more of this and adding some funding to this research. So, and then my personal experience, I'm not the traditional, I guess, research student at a lot of these. I grew up as a concrete finisher, laborer. My dad had a company. So I've been on a lot of really cool jobs. I consider myself very lucky. Did a lot of stamp work there. You can see a 100-yard slab on grade. So I try and offer a different perspective to this research, and I live and breathe concrete. I love this stuff, so I'm glad to be a part of it. But when we talk about recycling in New York State specifically, where and why is it favorable? If you look at the picture here, the green dots represent where counties where recycling is favorable and it's more common, and the red dots represent landfilling as a more common practice. So really the main areas that are doing a lot of recycling are in the Hudson Valley and Long Island. Our area is pretty red, but again, that's why we're doing this. We're pushing this, and going along with our research, Silica X out of Spokane, Washington, one of Alfred University's partners. Right now they're working to convert waste glass into a foam aggregate with high resistance to oceanic corrosion for retaining walls. So you can see on the bottom left there, that's some of what these retaining wall coupons look like, and those are currently being sunk into the Long Island Sound. So, but the current idea, basically using glass, recycled glass waste or alumina waste as an aggregate, replacement of fine aggregate, assessment of that concrete, and further optimizing the process from there. So you can see we have the recycled glass on the left there and the alumina waste on the right. So we'll get into this a little bit more, but the recycled glass especially, we didn't get the best samples for our original tests, which kind of influenced the data, and the same thing went for the alumina waste, but we got some better numbers later on, so we will talk about that. But it's a big deal. 50 billion tons of construction sand are excavated every year. So if we can offer different solutions and reach a similar strength, then this definitely does have its applications. But you can see this is us making the samples here. We did a 20-inch beam sample, and we did 2 runs of the alumina waste. We did 50% replacement of sand and 100% replacement. And then for the glass, we just, this project has been going on for 2 years. I stepped onto it this year. The first year we did all 100%. This year we were not able to get 50%. We weren't able to get more glass samples, so we just did 50% alumina waste. And we'll talk more about that. But yeah, we did, for the beams and the cylinders, we did 7-day curing, and then we tested them. So you can see the molds and the curing process there. And then this is our testing apparatus here. You can see some of the beams being crushed there. got pretty nice failure modes from them, so that was good to see. So looking at the results for 100% replacement of both alumina waste and recycled glass, you can see the plane got to about, the modulus of rupture there is about 420, 430. With the recycled glass, you can see we're sitting right about 330, so a little bit further down. And the alumina waste was between 281 and 340. So you may be asking, well, the standard says to do three samples. Why are there only two? And it's kind of a bit concerning because there's such a jump in the alumina waste. Well, we only had so much alumina sample and glass sample. We could only run 2 tests and make the best average out of it. So they're very busy over there at Alfred University. They have a lot going on, and a lot of their stuff is very cutting edge. So they did the best they could to supply us with stuff. But again, with the recycled glass, we see about a 21% reduction in flexural strength, and alumina waste about 26% for a 100% replacement. So, and again, a sort of similar story with the compressive strength. This was around a 3,000, 3,500 PSI mix plane. You can see the plane samples right around 3,500. With the recycled glass, we got to about 2,400 on average. And again, with the alumina waste, there was a bit of a gap there, with one sample being 1,700, the other being about 2,200. So again, overall, recycled glass reduced the compressive strength by about 31%, and alumina waste by about 43%. And then in terms of workability, we had about a 6-inch slump design. The recycled glass got to about 6.75, so a little bit higher. And then the alumina waste dropped quite a bit by 3 to 3 inches. So that's a 50% drop. For 100% replacement, we may want to look into some super plasticizers and things like that if you need more workability out of it. So now moving on to the 50% replacement. This was the part of the project that I was mainly on with the alumina waste. We saw very good numbers here. You can see that we saw about an 18% jump in flexural strength compared to the plane samples. So that was good to see. We had much better samples this year. We had a lot more uniform mix, so to speak. So I think that played a lot into it as well. So you can see these are our samples here. They had really good failure, in my opinion. They, nice crack right down the middle, and so yeah. And as far as compressive strength goes, again, it was very promising. We saw a couple hundred pounds gained with the 50% replacement as compared to the plane sample. And again, if you compare the 100% to the 50% replacement, it's pretty jarring. And so, but overall, we saw a 9% increase with the 50% replacement this year. So, yeah, that was good to see. And we look at our overall data here. In the future, we definitely want to get back to the glass and do 50% replacement there. Because, if you see the 100% replacement of AW to 50%, that jump there is pretty dramatic. And you look at the 100% of the recycled glass, we would hope to see with the proper samples another jump up there. So, it's very promising. And it's not, we definitely want to look at different mix designs and some of the other admixtures and if you can incorporate fly ash and things like that to help it out. And 50% or 100% replacement isn't necessarily the answer. 75% replacement, 80% replacement, further optimizing that. So there's definitely a lot of work to do in the future. As our research department is, we're kind of new to this and figuring things out. So, we're happy with where we're going, and we're very, again, grateful to Alfred University for their help, and we'll continue to work with them Another thing that we definitely want to look into with the glass especially is the alkali-silica reaction. This was, when the glass research first started to come out, this was definitely a big concern. A lot of it now kind of plays into the size of the glass, and I think that goes back to what I was saying about, getting good glass samples and incorporating that into the mix to help mitigate that. But again, that's something we're going to want to look into. Workability concerns, I don't, some of the different possible applications. So yeah, that's where we're at right now. And again, thank you to ACI, thank you to Professor Tabatabai for helping me out. Yeah, really appreciate it.